The agenda today is first we will have our presentation from Peyman, which will address the past, present, and future of MOFs with a particular interest in how crystallography and structural sciences can integrate with MOF research. We'll then have a brief Q&A, and finally we will have two 10-minute networking sessions. And this will be in breakout rooms where we'll be randomly assigned, and Peyman and myself, along with some of our other CCDC staff, will be joining in these breakout rooms to kind of facilitate the conversation and make sure everyone's having a good time. But I want to sort of give a brief note on some of the tools that we have available here at the CCDC to sort of help you with your MOF-related research. The first of which is our CSD MOF collection or MOF subset. It contains over 10,000 porous crystal structures. They're all three-dimensional, experimentally determined structures, generally for metal organic frameworks. And this is freely available to our academic users. And we also have over 100,000 MOF-like frameworks that are available in the CSD. So these are available with your license for the CSD. In addition, we also have two webinars listed here that are related to MOFs and porous materials. The first of which is given by Seth, who is a senior scientific editor. And the second of which is from Dr. Dave Fairen at the University of Cambridge. And we will distribute these slides after the talk and networking event today. So you'll be able to actually click on these links and go directly to these talks. But now I'd like to introduce our speaker, who is, again, Dr. Peyman Moghadam. He is an assistant professor at the University of Sheffield in the Department of Chemical and Biological Engineering. He's a co-author on several papers that you can view here. He joined the University of Sheffield in November of 2018, prior to which he was a senior research associate at the Adsorption and Advanced Materials Lab at the University of Cambridge, where he worked with Shell for developing MOF adsorbent materials for natural gas storage. Prior to this, he did a postdoc with Professor Randall Snurr at Northwestern University, and he completed his PhD at the University of Edinburgh. Over the last 10 years, he's closely worked with companies such as Shell, BP, Honeywell, Honda, Smont, and he worked with them to develop porous materials for different gas adsorption and separation applications. His research group's current focus is on combining molecular and process level simulations along with big data science to discover and engineer next generation nanoporous materials with an eye towards adsorption, separation, catalysis, sensing, and energy storage applications. With that, I'd like to turn it over to Peyman so he can go ahead and bring up his slides now. And I'd also like to thank him for agreeing to speak today for us.
Thank you, Jeff, for the kind introduction. So let me try to share my slides. So I suppose you should be able to see my slides now?
Yes, you can.
Okay, excellent. Hello everyone. My name is Peyman Moghadam from the Department of Chemical and Biological Engineering at the University of Sheffield. And as Jeff mentioned, today I'll be talking about some of our previous and current collaborations with the Cambridge Crystallographic Data Center to generate a database of metal organic frameworks or MOF structures. And then I'll talk about how we can use high throughput molecular level simulations to screen such databases for mainly gas adsorption and separation applications. So just to introduce my lab, in our lab, we work mainly with MOFs and other type of porous materials like COFs and zeolites. And we study them for different industrially relevant gas storage and separation applications. So I have previously, as Jeff mentioned, I have previously collaborated with Shell on developing MOFs for natural gas storage. Honeywell UOP for the adsorption separation of valuable chemicals like the xylene isomers. And very recently, my research group has started a very exciting collaboration with Svante in Canada, who are developing MOFs for commercial scale CO2 capture. And I have to say that in all these collaborations with experimentalists, what our group does, we aim to speed up the way new porous materials are designed and developed through computer simulations. We basically apply different computational techniques from grand canonical Monte Carlo simulations of gas adsorption to quantum calculations and molecular dynamics to help our experimentalist friends not only to better understand their crystal structures, but make predictions to guide their synthetic efforts towards promising materials. So I have to note that macroscopic performance of MOFs is highly related to microscopic structure and dynamics. We can model structures on the computer to shed basically more light on the crystal structures. This is particularly important on materials where it is difficult to obtain single crystal and the structural information always needs to be refined based on, for example, powder X-ray diffraction results. We also study adsorption and diffusion properties of gases in MOFs using different computational techniques, including GCMC simulations of adsorption, if you're interested in calculating the amount of gas adsorbed, heat of adsorption, density maps identifying those energetically favorable adsorption sites, adsorption selectivity, if you're dealing with, for example, multi-component mixtures. And in general, with this range of simulation tools, we can provide a detailed molecular or atomistic level insight on gas adsorption in porous materials. Okay, so I already mentioned MOFs a couple of times. And in these slides, we are basically highlighting some of their key properties. So MOFs consist of these metallic and organic building blocks. I'm showing these in this cartoon here that was made, I think, by Professor Chris Wilmer over 10 years ago. So these building blocks, they self-assemble to these beautiful 3D scaffolds. And the cool thing about MOFs is that by judicious choice of different building blocks, one can envisage almost limitless number of combinations. You can basically mix and match these building blocks to make new structures. So we have almost limitless number of ways we can actually combine these different building blocks. The same way we build things with Legos, right? So these structures, they have really high pore volume and surface area. The surface area can go up to 6,000, 7,000 square meters per gram. And this is amazing. If you think about it, this is the surface area of a football pitch in 1 gram of the material. You have pretty much tunable pore sizes in MOFs. So you can change the pore size according to the adsorbate of interest that you're trying to store or capture. You have accessible metal sites. These metal sites are important, for example, for catalysis applications or for gas separation applications. And most important of all, these are crystalline materials. So we know the atomic positions of each and every structure. And this is good news for us as computational chemists because we can actually model them on the computer. And I have to say, because of all these fascinating properties, MOFs have been mostly studied for gas storage and separation application. And this is what I'm showing in these cartoons here, where, for example, in this separation application, CO2 molecules in a stream of CO2 and methane are actually preferentially adsorbed. And the other compound is basically excluded from the porous system, as I'm showing in this cartoon here. Okay, so basically for the rest of this talk, I'm going to show you how high throughput molecular level simulations of many MOFs can help identify outstanding materials for gas adsorption applications. I will mainly discuss our recent work on a rare case of computational MOF discovery for oxygen storage, where we completed the full cycle for high throughput simulations of oxygen storage to synthesis and gas adsorption measurements. Excuse me. And you can run these calculations for other applications if you're interested, for example, in hydrogen storage or natural gas storage, or for other gas capture applications, for example, CO2 capture or the capture of other toxic chemicals, where some of the other research groups in the world are also active in some of these areas. Now, in order to do our high throughput adsorption simulations, we needed to know how many MOFs have been synthesized so far, and how we could create a single database or resource containing all the existing or already synthesized structures, right? And to do this, we teamed up with scientists from the CCDC a few years ago. So this was the work that we did when I was in Cambridge working with Professor David Fairen-Jimenez and his group. So here is the total number of structures deposited into the CSD from 1972 to 2016, reaching almost 900,000 materials. Apologies that this is not updated. I know that I think the latest count up to 2020 shows more than 1 million structures that are deposited into the CSD, the Cambridge Structural Database. And this database includes small organic molecules as well as MOFs and other porous materials. So what we did here was that we developed a number of look for MOF criteria based on IUPAC description of MOFs, and we managed to identify almost 70,000 MOF structures in the database, in which around 55,000 of these materials were non-disordered and around 8,000 were actually porous. And by porous, I mean a probe molecule with the size of nitrogen can actually fit within the pores of these structures. I note that we were not the first ones generating a database of MOFs. Other MOF databases exist, most notably the so-called computational ready experimental MOF database, or the core MOF database developed by Professor Randy Snur's group at Northwestern University, which have been extremely useful for researchers running high throughput calculations in MOFs. But I have to say the advantage of this CSD MOF subset is that it gets updated every time the CSD updates its structures every quarter, right? So if you are a chemist anywhere in the world, you synthesize a MOF today, in 3-4 months' time, when the database gets updated, your MOF structure will be automatically included in the CSD MOF subset. And I think, if I remember correctly, at the moment, we have nearly 100,000 MOFs present in the most updated version of the CSD MOF subset, and something of around 10,000 porous MOFs. So in a later work in this chemical science paper, what we did was that we also categorized MOFs into some of their most well-known secondary building units, right? So here in this slide, the green and red diagrams include basically the search queries in that we developed in Conquest that are labeled as must have and must not have for specific building blocks and their bond arrangement. So as you can see, we developed search criteria for 6 prototypical MOF families that are well studied in the literature. So you have the zirconium oxide nodes, which are a stable class of MOFs. You have the sort of copper-copper patawild and CPO27 like materials, which contain unsaturated metal sites that are interesting for gas separation and catalytic studies. You have the ZIF-like materials and structures containing zinc oxide metal nodes. I note that we really anticipate that these criteria introduce some guidelines for MOF researchers to perform quickly targeted MOF searches, not only for these classes of MOFs that I'm showing in this slide, but also for additional chemistries. Remember that these criteria can be really customized in CCDC's structure search software that is called Conquest to look for new MOF chemistries. I really encourage everyone to actually use these great tools from CCDC's software suite to explore the database and all these different chemistries. So we also classified MOFs according to their some of their well-known functional groups. So users will have now easy access to structures, for example, containing polar groups, or for those containing alkyls or alkoxy groups, and all these features are already implemented in the CCDC's Conquest. Okay. All right, so let me go back to the main focus of my talk on high throughput screening of MOFs for oxygen storage, right? So after we generate a database of MOFs, what we do is we normally use different computational tools to calculate different geometric properties of each and every MOF. This basically includes characterization of the BET area, pore size distribution, the largest cavity diameter, the window diameter, or the pore limiting diameter, as I'm showing in this schematic here. And you can also get some information about the the surface chemistry of these structures, which structures are non-functionalized, which structures are actually functionalized, and can we actually group them together? And obviously, I have to say that the characterization of all these different geometric properties, first of all, is extremely useful because it's much faster than experiment, and secondly, it provides valuable information about the expected adsorption performance of these materials. So let's take a look at some of these properties. So here we have the histograms for all the MOFs in the CSD MOF subset, and these are colored according to the years that they were actually deposited into the CSD from 1995 to 2015. You have the data for the largest cavity diameter, the pore limiting diameter, void fraction, surface area density, etc. And you can see that for a lot of these MOFs, you have a peak around structures with pore sizes of around 5 to 7, 8 angstroms, and surface areas of less than say 2,000 square meters per gram. And this is most probably because historically people were actually interested in developing MOFs for gas adsorption and separation applications. And for those applications, you need basically structures that interact strongly with your adsorbate molecules. And normally those MOFs, they have average to small pore sizes. Okay, so now we have the database ready. We have calculated the geometric properties of each and every MOF materials. We can actually go ahead and run high throughput GCMC simulations of adsorption to identify those materials that are promising for specific gas adsorption or separation applications. So this is what this cartoon was showing here. So let's look at some of the results that we get from such high throughput computational screening of MOFs for gas storage applications. So as I said, I'll be talking about this work that we published in Nature Communications a couple of years ago. And this is focused on oxygen storage. So in this graph here, I'm showing the deliverable capacity for oxygen gas. So the deliverable capacity is defined here. So you have the uptake at 140 bar minus the uptake at 5 bar, right? Because you want to use the MOF to basically adsorb and desorb the gas. So you're adsorbing at 140 bar, then you're desorbing at 5 bar. And this is plotted versus the heat of adsorption values. Remember that adsorption is an exothermic process, so you're releasing some heat. So every data point that you see in this graph is a result of a separate MOF material, right? And so if you basically count the number of data points, you count basically 22 structures. So I'm running these calculations for only 20 structures. And here you can see a little bit of trend here, but things are not very clear. The deliverable capacity seems to be increasing as you increase the heat of adsorption. But then if you further increase the heat of adsorption, it seems like that the deliverable capacity for oxygen decreases. So let's say things are not very clear, all these this structure property that we are looking at. Now, if I repeat these calculations that I did for these 20 structures, but now I do it for 3,000 materials. These are actually the materials that we took from the core MOF database, which are based on the CSD MOF, CSD structures. If I repeat this for 3,000 materials, my structure property graph becomes much more clear and will look will actually look like something like this. So now in this new graph, you can see that there is a clear peak in the oxygen deliverable capacity for materials when the heat of absorption is around 10 to 15 kilojoules per mole. You can also see the emergence of physical boundaries, right, of your absorption data cloud. So you know immediately that you wouldn't be able to design a structure with deliverable capacity of, let's say, 20 or 25 here with a heat of absorption of 20, basically a data point here. So we are getting some useful information about the performance limits of your absorption, okay? But if you look closer, you can see that in the same region of 10 to 15 kilojoules per mole, I have my outstanding materials that are all the way up here, but I have, you know, a bunch of rubbish structures with very, very low deliverable capacities all the way down here. Okay. So the question is, what is the difference between these structures? Like all these outstanding structures and all these structures that are not performing so well. Now, if I change the plot from a two-dimensional plot to a three-dimensional one, so I basically, if I color the data points or my MOFs according to a third property of my materials, which is the void fraction. The void fraction is the ratio of the empty volume over the total volume of your MOF, that goes from 0 to 0.9, you can clearly see that all my top performing materials in this region, they are shown by this purplish color, which represents materials with void fraction values close to 0.9, right? So this is now a three-dimensional graph. And I have to say, we can actually do better. I can go ahead and present my data in 4 dimensions. So basically, if I change the size of each data point or structure according to a fourth property, the surface area going from 0 to 5,000 square meters per gram, and again, you can immediately see that all those top performing materials are those that are represented with larger data points, which represents MOFs with large surface area values. So this is a 4-dimensional graph. And what I really like about these structure property graphs in general is their predictive power. So if my experimentalist friend comes to me and says, you know, I have made a completely new MOF material, and asks me, okay, how do you think it will perform in the context of this particular application, oxygen storage? The only question I need to ask basically my experimentalist friend is that, okay, what is the void fraction and surface area of your material? And if the answer is, okay, the void fraction is roughly around 0.5 and the surface area is around, I don't know, 300, 400 square meters per gram, you know, I can immediately see that, you know, a void fraction of 0.5 sits somewhere in this greenish region. Okay. So without doing any calculations, without lifting a finger, I can actually point towards the region where that particular material would perform for oxygen storage. And I can immediately tell my friend that, okay, your material is not going to be a good material for oxygen storage. Okay. So again, what is really interesting about these performance property graphs is that I can make a good guess of how future materials can perform. And obviously, these are very, very informative data analytics tools that can be applied to any multidimensional problems in the realm of materials design and discovery. And given the importance of this type of data analytics, we actually started developing a software where you can easily generate and visualize these beautiful multidimensional plots to analyze your data. We call the software Wiz, and to use it, there is no need for you to know any programming or coding skills. You just need to log into this website, wiz.chef.ac.uk, upload your data set on the website, and you can enjoy analyzing different structure property relationships using different multidimensional plots. So here is a quick demonstration of how the software works. Let me see if I can get this to run. So again, here you can see that you can basically, after you upload your multidimensional data set, you can play around with the sort of easy to use drop-down menus to explore different structure property relationships. I think for the oxygen work, over 1,000 unique structure property plots could be actually generated according to the user's interest for different pressures. We are also developing, let me see if I can play this as well. So yeah, we are also developing this tool, so you can actually within this platform you can plot your data in real time. So as soon as your simulation or if you have experimental setup, if you have, I don't know, robots that are IoT enabled and producing lots of data, you can actually visualize your data in real time. So as soon as the data is generated, you will be able to visualize and analyze it with this user-friendly tool. Okay, so I have only a couple of more slides. Another important output of high-throughput screening, I have to say, is that we can identify promising materials. So here I am showing again the structure property graph for the oxygen storage work. We have oxygen deliverable capacity in the sort of volumetric terms in the y-axis, and the gravimetric terms in the x-axis. The color shows the void fraction, and the size is the largest cavity diameter. And what you can do here, you can actually identify and highlight the absorption capacities for well-known MOFs, for example, MOF 74 or HCOS1. And you can also identify your top performing materials as well, right? So looking at this, the structure that we really liked was this UMCM 152, which has the highest volumetric deliverable capacity and is among our top 4 materials for the gravimetric deliverable capacity. So we really like this structure. And because we were doing all this computational screening on already published and synthesized structures, we went to basically identify the paper where the structure was published at was actually this structure with these building blocks. What we did at this point was that we actually sent exactly this slide to Professor Omar Farha at Northwestern University and said, okay, we have done the computational screening of all these MOFs for oxygen storage, and we think that this material has a lot of promise for the application. Can you make it and test it for us? Professor Farha said yes, and they made this structure. So one of the first things that the porous materials community do to characterize their materials is they calculate or run nitrogen absorption measurements. So these are the simulations that we did in Cambridge for nitrogen at 77 Kelvin. This is the nitrogen absorption experiments that Professor Omar Farha's team did at Northwestern University. we have a great match, which immediately basically tells me that the sample that we made is highly crystalline and has been successfully activated. And obviously we wanted to know how the structure basically works for oxygen storage. So here I'm showing oxygen uptake versus pressure. This dashed line shows how much oxygen you would absorb in an empty tank. So by simply just compressing the gas. This is the isotherm for NU125. This is the previous world record holding material before we did the screening. This is the simulated absorption isotherm for oxygen for UMCM 152. Remember that this was the material that we identified to be the best material to deliver oxygen volumetrically. And at the time, in Omar Farha's group, they didn't have high pressure adsorption equipment, so they couldn't go up to 140 bar to measure oxygen adsorption. So what they did was that they actually, when they synthesized the sample for UMCM 152, they actually shipped it all the way from Chicago to Florida to Micromeritics, so they can actually run oxygen adsorption measurements up to 140 bar. And this is what they measured. So as you can see, we have again a great agreement between simulations and experiments, especially at low loading and high pressures. And basically this material that we identified delivers 22% more oxygen than the previous best known material, NU125, and around 90% more than an empty tank. Okay, so I think I'm running out of time. I'm going to quickly summarize. I have to say that because of practical constraints, experimental trial and error discovery of materials is simply not fast enough. And therefore, more efficient alternatives must be developed to design and discover new adsorbent materials. And today I showed you that by employing high throughput molecular level simulations, we can quickly and accurately guide the synthetic efforts towards promising materials. And sometimes with a little bit of luck, you may also be able to find the best materials on the computer for a desired adsorption application. So at the end, I would like to basically thank everyone in my research group in Sheffield. We have some more exciting project. We started with a new joint PhD studentship with Dr. Jason Cole to characterize the topology of all the MOFs in the CSD MOF MOF subset, where we worked a lot with Seth, Susanna, Peter, and Andrew to make. Special thanks to Professor David Fairen-Jimenez and Aurelia for actually making the CSD MOF subset. We are also doing some exciting work with Professor Michael Reguera's team, the University of Vermont, where we are characterizing zirconium oxide MOFs for CO2 capture. And I would like to thank all the other funders of our group and especially the CCDC for giving me the opportunity to give a talk today. Thank you, everyone.
Yeah, that was great, Peyman. Thank you very much for that excellent talk. I think we have a few moments to answer a few questions. So if anyone has any questions they'd like answered at this point, please feel free to drop something in the chat. And if you raise your hand to kind of alert us maybe as well. It looks like we have one from Ashvin Famato. Sorry. Can we use this software to predict different molecule binding? Do you have any comment on that, Payman?
Sure, sure. We can definitely do that. So we can actually perform DFT calculations. So we can calculate the binding energies for different gases with specific building blocks of the MOF through quantum calculations or DFT calculations, right? So we can model part of the MOF. So we take a cluster of the MOF structure, and we can calculate the bonding energy of specific gases to those building blocks, or we can model the entire structure as a periodic material to do the same sort of calculations. We can also, through GCMC simulations, grand canonical Monte Carlo simulations of absorption, by calculating the different energetics between the gas and the MOF material. We can also calculate the heat of absorption, right, and sort of identify the hot spots and those energetically favorable absorption sites within the MOF as well. I hope that answered your question.
Thanks.